All right, today we're going to look at the other of the two ways of finding volume with integration, and the shell method is the one that we're on today. So starting with this, we're going to talk about kind of the idea behind this. So when we worked with the disk and washer methods in 7.2, we saw that our rectangular regions were perpendicular to the axis of rotation, right? And that's what you guys were having me draw on the board, yes? And then when we spun our shape, spin it around some axis or some line, we ended up creating a disk or a washer. Well, with the shell method, our rectangular region is actually going to be parallel to our axis of revolution, or axis of rotation. And when our region is spun, we're going to create a cylinder. And you'll see a great picture of that here in just a second. I'd like to actually mention one really nice way to remember which one's which, is because parallel rhymes with shell. So if you're doing the shell method, you're doing something that's parallel to your axis of rotation. Okay, so just one of those crazy things to remember. And what we're going to do is we're going to watch these videos in order. I'm going to hope I got them on here in order. I think so. Oh, and all right. All right, so we took a look at 3 different videos of how to sort of picture in our minds what this is doing, right? And the last video that we looked at was really good at showing you an example of why you absolutely can't just always go with discs and washers, and why that doesn't always work conveniently to even try. And so we're going to talk a little bit first about the descriptions that we looked at on this, on creating this volume and what these sort of equations look like. Okay, so the volume, as we established, or he established for us when we were looking at that, was found by taking basically length times width times height of a rectangular slab, right? And one piece of it was 2 pi r. A second piece was the height. And a third piece was the thickness. Right, so h was the height, the thickness was sort of our width, and then the 2 pi r was the length, if you want to do that. And we actually see that as the thickness goes to 0, we end up with 2 different formulas. And these are the formulas that we will use as we're trying to find these. So we're going to have that 2 pi, that will be present. Notice that's different than when we did discs and washers. What was in front when we did discs and washers? Just pi. Right? It was just a pi in front. Now we've got 2 pi in front. We'll have our integral. Our integral for the volume when we do a horizontal axis of revolution, I'm going to call it from C to D. That actually ends up being a function in terms of y. So this is r of y times h of y. Okay, so the radius in terms of y times the height in terms of y, and then it's dy. Okay? And then for the volume, when we have a vertical axis of revolution, this is 2 pi, and we'll go from A to B. This is the radius in terms of x, the height in terms of x, and then it's dx. So I used r of x and I used r of y, h of x and h of y. R of x and r of y is the radius, is kind of what I said, but it's the average radius, and then as their thickness goes to 0, it just becomes the radius, right? So as these become infinitely thin. And then the height is a constant. It's going to be h of y or h of x, the height of the shell. So we need to do an example, because we haven't seen an example actually finished on any of those videos that we particularly watched, right? So this is going to be a shell method. We're going to evaluate an integral that gives the volume of the solid, generated by revolving these 3 sort of lines, or equations rather, around the y-axis. So the first thing we need to do is, just like we did in the last section, we need to draw the representative information, okay? So we've got an equation, y equals 4x minus x squared. And you're welcome to put that in your calculator if you're not sure what that would look like or whatnot. It's actually, what general shape is that? What would 4x minus x squared's general shape be? A parabola, because it's got x squared in it. Is it a parabola opening up or down? It's down, because the x squared is actually negative. And the image, I should have made this a little bit longer, so let me do that. That didn't work. All right, the image looks something like this. Almost like the sine curve that I put up beforehand, right, Hannah? But it isn't for sine. So this is actually y equals 4x minus x squared. And it goes from x equals 0, which is the y-axis, correct? Out to y equals 4, or I'm sorry, up to y equals 4. And if you actually look at this equation and you plug in y equal 4, we can actually see that that's going to occur at x equal to 2. And so I'm actually going to show you how that works with the algebra for it, just in case you don't remember. So I'm actually supposed to be letting y equal 4. So this is 4 equal 4x minus x squared, right? And we would get that all on the same side, so I'll put everything on the left. X squared minus 4x plus 4 equals 0. How do I solve this? Factor, yeah. Need to factor. And how will it factor?
X minus 2, x minus 2.
Yeah, it's actually a perfect square, isn't it? So this is x equal to 2. So this actually achieves a height of 4 at x equal to 2. So this is my image right here. So actually at 2, I am up here at 4. Okay. And what that image then gives me is that I'm supposed to be trapping my area between, let's see, we drew x equals 0 in there, that was the y-axis, and y equal 4, which is this piece right here, and my curve, which was this piece right here, and of course it keeps going, but the trapped area ends up being this piece right in here, right? Are you with me? You got to know which area you're trapping. That's the first issue. Second issue is instead of we're rotating around the y-axis. So I'm rotating like this. Do I draw a representative rectangle that is parallel or perpendicular? Parallel, because I'm working with shells, right? So I need a parallel representative rectangle. So my rectangle looks something like this. So far, so good? Now, this rectangle is rotating, and as I told you, I'm no good at drawing these pictures, so we're going to work without them, but we still have to be able, or we still can identify the pieces of information on the picture, just like we did with discs and washers, okay? In other words, my height is actually right here, yeah? In blue. That's my height. And we worked with things like this in the last section. What is that height? Yeah, it's 4 minus y. We'll come back and fill that in a minute, okay? And then I need the radius of my cylindrical shell. The radius is this piece down here, from here to here, right? So the radius is actually equal to what? It's actually x in this diagram. So my radius is actually x. And then what else do I need? Oh, I need to know if I'm dealing with dx's or dy's. So, yes. Because x is going to be the distance from the center out, and we're looking at a horizontal distance, and that's x. So one of the things he did on his picture, let me use another color, is that he put a dot right here. And this dot right here was the point xy. So the distance away from the x-axis, or from the y-axis is x, and the distance up from the x-axis is y. So this distance that we've moved over is x, okay? And it always is. It's just that sometimes we're dealing with dx and sometimes we're dealing with dy, so we have to be a little bit careful. So we're taking a look then at whether we're dealing with dx or dy. And if you aren't sure, you can go back to what this slide was telling you. Are we dealing with a horizontal axis of revolution or a vertical axis of revolution? It's vertical. This is the y-axis, right? So as far as this description is concerned, I'm dealing with dx. Now, as far as my picture is concerned, it also makes sense that it would be dx from the same perspective as the videos we looked at last time, right? This distance, or this is delta x right here. The width of my representative rectangle is a distance in terms of how wide x is, correct? So it's the same idea from there. So I'm dealing with dx on this problem. So we've identified all of my features, and we're going to go back up here one more time, and Cameron tried to tell me this, and I told him, whoa, just a second. This piece right here, this height, is the only one that doesn't have only x's in it, right? So this says it's supposed to be 4 minus y, and what is y? So it's supposed to be 4 minus x squared. And I'll fill that in on the next slide as well. Did I write it wrong? 4x, there we go. I did write it wrong. 4x minus x squared. Okay, so let me write all that sort of more clear. So we said we have the volume. It is 2 pi. We'll work with our limits in a minute here. It's supposed to be the radius, r of x, times the height, h of x, times dx. And it's going to go from some a to some b that we need to identify. So we already said that the radius was x. The height is 4 minus y, and y was 4x minus x squared. The dx at the end. This is an integral, and it needs to be the limits of integration on x. And I'm going to go back to the previous screen so we can look back at that picture to do that, okay? So if you're still writing, just hold tight for a second. I'll come back to the screen. This is supposed to be that shaded region's value for x. Where does x start and where does x end? 0 to 2. And that's actually why I needed to find this x equals 2 business down here, right? So this will start at 0 and it will end at 2. And that's the hard part, because this is very clean to take a derivative, antiderivative of, after we clean it up. And we do need to clean that up before we get too much further into this. So let's take a couple minutes. So I have 2 pi. I have an integral from 0 to 2. This is x. And then inside right now I have 4 minus 4x plus x. Sorry, plus 4. Oh, shoot. What did I do?
Not a clue.
Okay, I think I fixed it all. All right, so then it should be plus x squared here at the end, right? All right. We need to do one more thing. What do we need to do? Somebody say it so I can do it. Yeah, I need to distribute that x, right? So I've got 4x minus 4x squared plus x cubed and all of that dx. And now that it's cleaned up, I need to take an antiderivative. So somebody help me. What's my antiderivative going to be? 2x squared. Somebody else for the second piece. All right, so 4x cubed over 3. And then the last piece, somebody new. What'd you get, Emily?
Hold on.
Do you have it, Kendra?
1/4.
Yeah, so we've got x to the 1/4, and we've got divided by 4 times 1/4. So x to the 4th, rather, times 1/4. So this is what we have, right? Evaluate at 2 and 0, and I don't know about you, but this one's really friendly to evaluate at 0, because what happens when you plug 0 into all of these? You get nothing. And that we've been working with polynomials, which is why that's been happening a lot. That doesn't happen with all functions. Obviously, if we had an exponential function or a logarithmic function, we wouldn't be getting zeros on all of it. But most of the ones we've been dealing with so far, we have. So this is 2 pi, or even trigonometric ones we wouldn't either. So I'm supposed to be plugging in 2. So this is 2 times 2 squared minus 4 times 2 cubed over 3 plus 2 to the 4th over 4. And then all of that's actually minus 0, and then multiplied by my 2 pi. All right, so let's do this piece by piece, because this is where we made mistakes last time when I was recording. We had, what's 2 times 2 squared? This one's 8 minus, what's 4 times 2 cubed? 32 over 3, right? And then what is 2 to the 4th? 16 divided by 4 is 4. All right, so somebody's going to grab a calculator, and then of course I have my 0 there. Somebody's going to grab a calculator, and they're going to take 8 minus 32 thirds plus 4, and tell me what you get. 4 thirds? That's right. And then I've got 2 pi out in front, so this is 2 pi times 4 thirds for a grand total of 8 pi over 3.
I didn't trust my math.
It's okay. All right, so I know we have a lot of steps of what looks like calculus here, but really most of that was algebra, right? It was cleaning up what was inside, and even that wasn't complicated algebra. Agreed? The complicated part is the setup. Okay? So let's take a look at the next one. I don't think we'll have time to solve it, but we do have time to probably at least draw a picture and sort of imagine what it's going to be like when we set it up. So we've got a shell method problem again. We're revolving the equation y equals x cubed from x equals 0 to y equals 8. Those are our sort of bounding areas. And we're doing this with the x-axis this time, so that is the opposite of what we just did, imagining, right? All right, so we have y equals x cubed, which looks something like this. I have the line x equals 0. Where is x equals 0? What is that? That's the y-axis. So I'm doing this piece. I'm doing this piece. Of course, it continues down here as well. And not quite like I just drew, but something. And then I've got, I'm supposed to have x, or y equals 8. So what kind of a line is y equal 8? Okay, so Cameron's drawing a horizontal line in the air for me, and it's up here somewhere at 8. So here's my line y equal 8. So do you see the trapped area? It's got to be trapped between all 3 of those red lines, which means the area that I'm trapping is this piece right here. Agreed? Okay. Now, we are supposed to be revolving this direction this time. So what will my representative rectangle look like? Will it be horizontal or will it be vertical? It will be horizontal. It'll look like this. Okay, are we doing so good so far? Okay, so the height is actually right here. Okay, because it's the height of the rectangle. And we've got the radius of the shell. So the radius of the shell is actually this piece right here. That's my radius. And the point, kind of like what he did on his video right here, is the point, of course, x, y. So my height is actually x and my radius is actually y, isn't it? Yes. Okay. Well, let me make one other comment that I actually lied just a bit in how I drew this. I actually want the radius. No, I didn't. I drew it right. I take it back. I didn't lie. I was telling you the absolute honest truth for today anyway. All right, where are we? Okay, so we had mentioned that our radius is, oops, let me get the colors back. Our radius is actually x, and our height is y. And I'm supposed to be doing this with a horizontal axis, yeah? And you can also imagine from your picture here, if you don't want to use a formula sort of perspective, this is actually delta y from a visual perspective, yes? So my integration, which I'm going to try and get set up before we're done today, is actually going to be a dy on this one. Yeah? Yeah. And I'm supposed to take my radius in terms of y, my height in terms of y, and I'm supposed to go from C to D. Now, almost all of those pieces I have in terms of y, but not all of them. Which piece do I not have in terms of y? The radius. Right now my radius says that the radius equals x. How do I find out what x is in terms of y?
solve.
Right, I mean, I have an equation that relates them, and it's exactly the red curved equation that I drew anyway, which has the point x, y on it. I mean, so that is my y. My y right here, oops, let's try it this way. My y right here is found by my equation y equals x cubed. That's what it is. So I can take this equation y equals x cubed, and just like Dylan said, I can solve it for x, right? So what is x? Cube root of y. Or if you'd like to write it, because we're going to do it here in a minute anyway, you could write this as y to the 1/3, correct? And that actually works better for taking an antiderivative in a minute. So I'm probably going to leave it written that direction. So my equation that we're going to be setting up is going to take the radius in terms of y, which we just said was y to the 1/3, times my height. What was my height? It's actually y times dy. My limits of integration, though, need to reflect that they agree with y. Yeah? So what will my y start at and go to? 0 to 8, right? That's my y values, sort of minimum and maximum. So I'm going to be going from 0 to 8 on this one right here. So here we're going from 2 pi from 0 to 8. I think we have time to finish this. What's y to the 1/3 times y? Nobody remembers. 4/3, right? This is 1/3 plus 1. That's 4/3. Y to the 4/3 dy. Okay, so how do I integrate y to the 4/3? Okay, so the y to the 4/3 becomes y to the 7/3, right? So we can either divide that then by 7/3, or we could multiply by 3/7. Everybody okay with that? It's just using fractions within that rule that you guys already know and use all the time. 8 and 0, again, 0 is fabulous. Works great. The other thing here is, let me go ahead and write this as 6 pi over 7 at front. And then I'm actually got this y to the 7/3 is actually the same as the cube root of y, which we're now letting be 8, and then raised to the 7th power. Isn't it? You guys remember that? Y to the m over n is the same thing as the nth root of y to the m. It will be, yeah, just a second though. I'm going to show that. And so then this would be the cube root, of course, of 0 to the 7th, which is 0. All right, so what's the cube root of 8?
3.
No.
2.
2 would be right. And then if you take 2 to the 7th, then you will get 128. And you can do that on your calculator. I mean, that would be okay. But this is 128. So this is 6 pi over 7 times 128. And I think I have written down that that ends up giving me 768 pi over 7. Any questions about that one? Okay, so we did the x-axis, we did the y-axis, although not in that order. And then we're going to do one more axis next time. And you can take a look real quick. We're actually going to rotate it around the line x equals 4. Okay, so we'll pick up there next time.